So we have this problem right here. This is a dynamics problem. Try it out for yourself first, and if you get stuck, I'm here to help. So, with these kind of problems, there's steps that we should always follow. First, we should do a free body diagram. Next, we will do a kinetics diagram, and last, we will do a summation of forces and moments. And with this, you would have enough information to solve the problem. And before we get started into these steps, let's just figure out what's going on here exactly. So we know that this cart is going in this direction, being a force being applied to cause it to accelerate, and because of that, friction is also pushing this cabinet in this direction. And if you can imagine, if you push this cart hard enough, it will accelerate to where this cabinet will tip over in that direction, and it will tip about this left leg. So just keep that in mind when solving the problem. So let's get started with our free body diagram. Let's get into the steps. Alright, so we have point G here. That's given. So what forces are acting on our cabinet? And right now we're only focusing on the cabinet. We're not focusing on the cart. We know that gravity is being applied to it. And I'm putting M1 because that would be the mass of the cabinet. We know that there's normal force here and here at these two legs, and that would be N1 and N2. You'll see why these normal forces are different later. And last but not least, we have our friction, which would be pushing it in this direction, and then that would just be F. So that's all for our free body diagram. Let's state our coordinates. So we have Y and X. And then let's start our kinetics diagram. We know that this cabinet is moving to the left, so we would have M1A, just like that. And you might think that it would have a moment this way, kind of like that. But actually, it's just asking when it's about to tip, not when it's in the motion of tipping. So it won't be moving in this case, so we won't have any moment on our kinetics diagram. So that's it for steps 1 and 2. Let's start doing our summation of forces and moments. Let's start with summation of forces in the x direction. So on our free body diagram, we have F. That's it. And on our kinetics diagram, we have M1A. Let's do our summation of moment forces in the y direction. So on the free body diagram, we have N1, we have N2, and then we have M1G, which is going down the negative direction. And on the right kinetics diagram, we have 0. Let's do our moments. And let's do it about G. Really, you could do your moments about A, or you could do it about any other point on this cabinet, and it will give you the same answer. So that's how it works in dynamics. You could do your moments, and same thing with statics too. You could do your moments, summation of moments about any point, and it will still give you the same answer. But I'm going to do it about G because that's what's easiest for me. So let's do it about G. On the left side, free body diagram, we have the friction, and that would be moving it in this direction, so that would be positive. So friction, and the distance from friction to the point G would be this distance, which is 0.8. Then we have N1, which would be moving it in that direction, which is clockwise, so that'd be negative. And the distance would be from here to here, which is 0.7. So N1, 0.7. And then we have N2, which is the same as N1, except it would just rotate it in the opposite direction. So that would be N2, 0.7, and that would be positive. And on our kinetics diagram, we don't have a moment, so that would just be 0. Alright, so now, in order to solve these for unknowns, we have to have the same amount of unknowns as equations. We have 3 equations, but actually we have 4 unknowns. So we have to dig a little bit deeper to figure out what we could do to get less unknowns. So if we look at the problem, when this cabinet is about to tip, that means this leg, the right leg, will be lifting up. And if the right leg is lifting up, that means there's no contact being made at this point. So the normal force here would be 0. And in our case, we have N2, so that would be N2 equals 0. So we could eliminate N2 from all of our equations. So we don't need N2 here, we don't need N2 here. So let's just erase that. And this is what we get. Now we have 3 unknowns and 3 equations. So let's solve. Alright, so we just need to replace our given values with what we have. So M1 up here is 70 kilograms. So F equals 70A. N1 equals M1G, which equals 70 times 9.81, which equals 686.7 newtons. So yeah, you just calculate that with your calculator. So we have N1. And then with N, since there's only one unknown in this equation, now it's only F, and we know N1. F would be N1 times 0.7 divided by 0.8, which would give us 600.8625 newtons. So you just calculate that with your calculator as well. And last but not least, we have our acceleration, which is up here. And since we know F, our acceleration would just be F divided by 70, which is A would be 8.5835 meters per second squared. Alright, so we have all these. Alright, so what do we do with this information? This is useful right here because we know that this cabinet will have to accelerate 8.5835 meters per second in order for it to tip. And this force would be causing that acceleration. And so we need to find how this force will create that acceleration. And obviously we would just use this equation right here. But F, and in this case, F would be P. M would actually be, it wouldn't be just the mass of the cabinet, because P is being applied to this entire system, not just the cabinet. So we need to consider the mass down here as well. So that would be M. We'll just call that M2. And then A, we already know A, which is right here. And so M1 plus M2, that would be 70 plus 10. So that would be 80. And we have A is 8.5835, which gives us P as 686.7 newtons. And that would be our answer for P. And so that's for part A. Or that'll just be for the first part of the question. Now the next part, what coefficient of static friction is necessary to ensure that tipping occurs without slipping? So we know that in our problem, we have this point. We never considered slipping, so we'll just use the equations we had up here. So which equations involve friction? These two do. I'm just going to use this top one right here because it looks easier to deal with. So let's get that equation down here. Alright, so we know that friction, this is friction. We know that friction equals coefficient of static friction times the normal force. And we know the normal force that the cabinet is experiencing. That would just be N1. We know M1 and we know A. So that would mean that the coefficient of static friction would be M1A over N, which is 70. And then A, what was A again? Here's A, 8.5835 over N. And N was right here, 686.7. And that would give us coefficient of static friction of 0.87497 and that would round to 0.875. And the coefficient of static friction, or mu s, would be unitless, so this would be our answer for the coefficient of static friction. And yeah, that's pretty much it. Let's walk through what we did again. So of course we determined our free body diagram, kinetics diagram, and then our summation of forces and moments. We had to dig in deeper and figure out that N2 was equal to 0 in order to find our unknowns. And with our unknowns, we found out that in order for this cabinet to tip, it had to experience a certain acceleration, and that acceleration would be caused by this force, but that force was applied to the entire system, not just to the cabinet. And so we had to add those two masses up in order to account for the entire system in our F equals ma equation. And using that, we found P. And to find the coefficient of static friction, we just went back. We reused one of our equations right here. We replaced F with mu n, and using what we knew, we were able to find mu s, which is the coefficient of static friction. So that's pretty much it. If you have any questions on this problem, just comment in the comment section down below. I'll try my best to answer them. And yeah, that's pretty much it. Thank you for watching. Don't forget to like and subscribe. And yeah.